Hi, my name is Richard Wade and I'm a Principal Cloud Architect with Professional Services at AWS in Singapore. One of my areas of interest is performance engineering and especially network optimization. So today I would like to talk about some of the things that you can do to improve the overall network performance of your applications on AWS. In this session, we will cover some introductory concepts and solutions, but overall, it is designed for an audience with a good understanding of cloud architecture, systems, and networking. In order to understand how we can improve the performance of our applications, we need to first understand some of the underlying mechanisms which influence things such as response time and speed of data transfer. You've probably heard of the Transmission Control Protocol, TCP, and are aware that your applications use it for the reliable transfer of data between your AWS services, application servers, and your customers or users. In this session, we will present some detail on how TCP functions at a low level and how we can engineer solutions to maximize its performance. With this understanding of TCP and the aspects of networking which directly affect our application's performance, we will then look at our AWS service architecture. Specifically, how we can use AWS Edge services to select and design the right infrastructure to improve overall performance. Finally, with an understanding of TCP and having selected the right infrastructure to deliver our services, we will take a brief deep dive into how we can tweak and tune our application servers to get the highest throughput and most consistent performance. Before we can understand how the TCP protocol affects our application's connections, we must first understand how we can categorize these connections and how they differ in their requirements of the application server, the operating system, the network, and our overall cloud architecture. Firstly, mice. Yes, this isn't a joke. One of the ways we can classify TCP flows is by their relative size and duration. The name mice was given to those small flows which transfer a small number of bytes, maybe in the tens or hundreds of kilobytes. The vast majority of connections on the internet are small, and this means that they're also short-lived, starting and stopping quickly in just a few seconds. Even though HTTP2 allows us to multiplex object requests onto a single HTTP connection and TCP flow, we still have many web applications which open a very large number of TCP sockets in order to communicate to servers on cloud platforms. This means that a single application can create many individual mice flows of TCP. If we think about short-lived connections, which are transferring a comparatively low number of bytes, we can imagine that they would benefit from getting established quickly and achieving maximum throughput in a very short period of time. We can also imagine that if a short connection is disrupted by slow networks, lossy networks, and having to slow down and retransmit packets of data, then when considered on a large scale, it would result in a highly inefficient service and a very poor user experience. Whereas we can call small connections mice, a common term for large connections is elephants. The thing to note is that while the majority of the number of connections on the internet are mice, the majority of the data volume transferred is in elephant flows. Elephant flows are, as you can imagine, very long-lived and transfer a large volume of data. This could be in the hundreds of megabytes, gigabytes, or even terabytes. For such flows to perform well, they require an efficient network connection, which will give them a fair share of the available bandwidth. Packet loss does have a notable effect on these long-lived connections, and we will now look at how TCP works in order to understand why this is. So that we understand what we can do to improve application performance, we will take a brief deep dive into how TCP establishes connections, accelerates the rate of transfer, and responds to and recovers from packet loss. Firstly, let's look at connection startup, or how long it takes for TCP to establish a network connection. You may already be aware that TCP protocol provides reliable data delivery. What this means is that every packet of data that you transmit between a TCP client and server is guaranteed to arrive because each packet has a sequence number which is acknowledged by the receiver once it arrives. In order to establish a connection with a server, TCP performs what is commonly known as the three-way handshake. This consists of the sequence you can see on the screen: the SYN, SYN-ACK, and ACK. Firstly, the client, which could be your user's application or web browser, sends a TCP synchronized packet to the server. This packet is acknowledged by the server, and the client acknowledges that acknowledgement. Once this handshake is complete, the TCP connection moves into the established state. The application or web browser can then proceed to send its application layer requests, such as a HTTP GET or remote procedure call. The important thing here is the network latency between the client and the server, and this will also be very important to note when we come to discuss overall TCP connection performance. If the latency between the client and the server is high, for example in this case we have 50 milliseconds one-way latency or 100 milliseconds round-trip time, then this three-way handshake can take some time, in the region of 150 to 200 milliseconds. This is before the application can start to send its requests and begin responding to the user's actions. So as you can see, a responsive application is very dependent on the speed of this handshake taking place, and therefore the round-trip time between your users and the application server. Now we can look at what happens once a connection is established and TCP tries to increase the rate at which packets are exchanged between the server and the client. In this phase, TCP is trying to quickly discover the network capacity available on the path between the client and the server. It does this by doubling the number of packets it transmits each time it receives a successful acknowledgement for the ones it has already sent. Looking at the diagram, you can see that it starts off with one packet. When this is successfully acknowledged, it transmits 2 packets, and so on. TCP keeps track of the number of packets it is sending at any one time with a variable known as the Sender Congestion Window, or CWND. The key point to bear in mind here is that if you only need to transfer 100 kilobytes or 200 kilobytes of data, then your TCP connection may never reach the full capacity of the network path, as it'll spend its entire lifespan in this startup phase trying to reach its maximum potential speed. This is a significant problem for mice, but not for an elephant connection, which spends only a fraction of its time in startup. For elephants, the steady state performance of a TCP connection is much more important. So what happens when TCP reaches the capacity of the path between the user and your server? Well, normally this results in one or more packets getting dropped or lost in transit, which means that the receiver will only acknowledge packet sequence numbers up to the point of loss. When this happens, traditional TCP will reduce its transmission rate by halving the congestion window or transmission rate. Evidently, for short-lived or mice connections, this has a dramatic effect on the efficiency of the connection. And for long-lived connections, as we will discuss now, it can also have a big impact over the course of the connection's life. After experiencing a loss or timeout, traditional TCP enters what is known as the congestion avoidance phase and is common during steady state. This means that the TCP algorithm is now trying to avoid the packet loss it experienced while rapidly increasing its transmission rate in the startup phase. It does this by incrementally expanding the congestion window, just adding one additional packet to it each time it receives successful acknowledgements. So we can see in the graph that this results in exponential growth during the startup phase and linear growth during the congestion avoidance phase, which takes place after packet loss and the connection has discovered the capacity of its network path. Again, different TCP algorithms do things differently and use different metrics to measure what they understand to be the bottleneck on a given internet path. However, if we take traditional TCP as an example, we can see how slow recovery can be from packet loss if an elephant connection has to halve its transmission rate and then slowly increment back to where it was. If transmitting at hundreds of megabits or even gigabits per second, you can see how this can drastically affect the performance of an application over its lifetime. In fact, this graph was presented in a network performance session at reInvent 2017, where data was collected to show how quickly the throughput of a TCP connection drops as the percentage of packet loss increases. You can see that at 0% loss, we are achieving 100% of the possible throughput. But at just 1% packet loss, we are at 50%. At 2%, we're at 20% performance, and so on. This underlines how significant packet loss is to the efficiency of TCP, and when combined with round-trip time, you can begin to understand how high latency then affects the time it takes to recover from loss. The main takeaway for this section is that TCP is important to your applications, and the latency and packet loss are important to TCP. With the vast majority of your applications using TCP, it is important to understand how this protocol fundamentally works, and how the responsiveness and performance of your applications is completely dependent upon it. High latency will affect how quickly your users can connect to your application, how quickly they can send requests and actions to its user interface, and how quickly data objects can be returned to them. In the case of large transfers, there is a formula called the bandwidth delay product, which describes precisely the maximum potential throughput you can achieve using TCP between a server and a client given a certain round-trip time and available network bandwidth. And there is a link to an explanation of this formula at the foot of the slide. Fortunately, as a cloud architect, application developer, or systems operator, there are 3 things that you can do to directly influence the performance of your cloud applications. Number 1, you can design a cloud architecture which takes advantage of the features, facilities, and infrastructure available. This might be selecting regions close to your users, or it could be leveraging some of the managed edge services that AWS has to offer. Number 2, when it comes to choosing between the detailed options available to you when designing the infrastructure for your cloud platform, you can choose specific instance types or edge services to increase the throughput, or in certain cases place high-performance edge compute closer to your users. Finally, number 3, if you fully understand your application, your network environment, and your user behavior, you can begin to tune your infrastructure to suit the application, the infrastructure, and the architecture you've deployed. Let's start with number 1. Firstly, let's talk about how you can design an architecture to get your applications closer to your users using AWS Edge services. Whether your users are globally distributed or reside within a given region or continent, the Amazon CloudFront Content Distribution Network has 216 points of presence around the world. In these locations, we can position and deliver static content objects closer to your users and even carry out intelligent functions at the edge using Lambda at edge. Given what we've just been discussing with regard to TCP, let's see how CloudFront helps reduce the latency and improve the connection performance to our users. Let's consider an example where we have an origin server which has a round-trip time of 150 milliseconds from our users. As we saw earlier, assuming 1.5 to 2 round trips to fully establish a connection, it means that every new connection is in the region of 300 milliseconds before the first application request is received by the server. Similarly, consider how that round-trip time will affect the clocking of TCP's startup phase, and therefore how quickly connections will get up to full speed. So how does a CloudFront Edge cache help with this situation? Well, in many cases, a CloudFront Edge cache can reduce the round-trip time to your users to 30 milliseconds or less, which is a significant improvement. This means that an application request could be sent to our service within 60 milliseconds rather than 300 milliseconds without the cache. Generally speaking, the way that a content delivery cache works is that static objects are pulled from the designated origin server the first time they're requested. So we can see here that the first user would have the same experience as if there was no cache in place. The request would be made to the designated URL, which arrives at the CloudFront Edge cache. The cache, in turn, fetches that content from the origin and returns it to the cache, which returns it to the user. However, once the content is present in the cache, having been fetched once, it can now be delivered directly to further users, bringing the round-trip time for content responses down to 30 milliseconds. We can see in this diagram how the first user will experience the full 30 plus 120 milliseconds round-trip time as content is fetched from the origin server, but that subsequent users will just experience a 30 milliseconds round-trip delay in requesting content directly from the cache. This results in a significantly more responsive service and much more rapid delivery of content, as TCP can firstly establish connections much more quickly, and secondly, scale its transmission window. There is the added advantage of having a shorter network path to the user, which results in lower probability of congestion and packet loss. Overall, this means that smaller application objects can be very efficiently and quickly delivered from the CloudFront Edge cache. When it comes to larger objects, there are similar benefits. Due to the lower round-trip time between the users and the edge location, the transmission and acknowledgement mechanism will function much more efficiently, which results in a faster startup and growth phase, as well as faster clocking when in steady state, and therefore higher potential throughput when we consider the theoretical maximum of the bandwidth delay product. Reducing the latency between your applications and your users is one part of the equation. The other part is giving your applications the necessary potential throughput to packetize and transmit data at the rates you require. Not all applications and connections are between a web service and users distributed across the internet. In many cases, AWS customers have more complex applications, which require high-performance TCP connections between both local and remote instances, with very high packets per second throughput. Firstly, cloud architects should be aware that 9K jumbo frames are available within VPCs and to VPC peers. This means that each packet that is put onto the wire by your EC2 instance can be up to 9K in size. And I've provided a link on this slide which will take you to the documentation on aws.amazon.com, which explains in more detail how to make use of this feature. For the purposes of this discussion, we're interested firstly that you're able to enable jumbo frames, but also if we do need very high packet throughput for applications such as clustering and high performance computing, that there are infrastructure design options which can help deliver the throughput we need. Some of you will have hopefully heard of the AWS Nitro System since it was announced at AWS reInvent in 2017. However, for those who aren't aware of what Nitro is, I'll give a brief overview. In summary, the AWS Nitro System is the current generation of our hardware and hypervisor virtualization platform for AWS EC2 services, and aims to provide performance that is close to running your applications on bare metal. From a networking perspective, Nitro improves on previous generations by optimizing the data path between customer instances and the physical network. It does this using a very thin KVM-based hypervisor layer and a dedicated purpose-built Nitro hardware card, which combines storage, networking, management, monitoring, and security. This optimization results in three things that we're very interested in for engineering our application performance: improved throughput, improved latency, and improved packets per second. And as you can see in these comparative measurements published by the AWS Enterprise Strategy Group, Nitro-based systems can provide meaningful improvements in performance across the board, in terms of throughput up to 90 gigabits per second, internal latency down to 27 microseconds, and capacity for over 5 million packets per second versus just 1 million for the closest measured competitor. Here, you can see how Nitro-based systems compare with other EC2 instance types. For comparison, we have the T3 instances shown at the top left, and standard C5 instances shown in the top right. At the bottom, highlighted in orange, you can see the C5N, with N for Nitro, and the relative performance metrics with instance types capable of supporting up to 25 gigabits per second as standard, and sustained 50 or 100 gigabits per second on the larger instance types. But what if you want high network performance in very close proximity to your users? What if you need to deploy workloads which require low latency access to on-premises systems, to do local data processing, or to access local data storage? AWS Outposts are now available as a fully managed service which extend AWS infrastructure, services, APIs, and tools to data centers, co-location spaces, and on-premises facilities close to your users, applications, systems, and data. AWS Outposts run the same Nitro hardware that you run in your AWS region-based EC2 instances, such as the C5N, and can be linked to your AWS account in regions across the US, Europe, Southeast Asia, and ANZ. AWS services are deployed to the Outpost using the same AWS console and APIs that you use today with standard AWS regions. In this section, we've discussed how you can improve network performance for both region-based workloads, such as those in clusters or VPCs, as well as those based on new edge services, such as Outposts, where we can take that same high-performance compute and networking infrastructure and co-locate it with our on-premises applications, data, or users in order to significantly optimize the architecture. With this in mind, think about how a significant reduction in round-trip time down to the single-digit milliseconds, combined with optimized networking hardware, can improve the responsiveness, TCP throughput, and transfer rates of your applications should that degree of performance be required. Finally, let's look at how we can use our knowledge of TCP performance to tune and optimize our cloud infrastructure. In this final section, we'll use an example multi-region EC2 deployment to highlight some of the characteristics of different TCP implementations and some of the kernel tuning options available, which may or may not improve the performance of your applications. I say may not because it's very important to understand that there is no one recommended set of parameters which is guaranteed to improve all application types or traffic patterns. If there was, it would be the default settings. In practice, the default settings are made that way for a reason, which is to ensure a stable, balanced level of performance for the widest possible range of applications without causing problems for the server operator, the application user, or the network administrators. Therefore, if you do choose to experiment and tune your systems, please do so safely, in non-production environments and in a controlled manner. With that in mind, let's look at the experimental setup. For these tests, I created two VPCs, one in US East 1 and one in AP Southeast 1. In each VPC, I created a C5N 9 extra large instance using standard Amazon Linux 2 AMI, and I peered the VPCs. In AP Southeast 1, I have an Amazon SageMaker notebook, which I will use to analyze data written to an S3 bucket by the performance measurement software iPerf3. iPerf3 is a commonly used tool to measure network performance between two hosts and is popular in the network operations and TCP performance community. To run iPerf3, we run it with the -s flag on the server side, and on the client side, we use the command shown on this slide. We provide the server IP address to the -c flag as the traffic's destination. In this case, we're going to transfer 1 GB of data, and I'm asking it to output a JSON formatted log entry every 200 milliseconds with information about the TCP connection and data transfer in progress. Note that the round-trip time between hosts is around 220 milliseconds. This means we should get a log entry roughly every round-trip time. So what are we going to test? In the time permitted, I'm going to show the measured differences for some key TCP values which we can easily tune in the Linux kernel. On this slide, you can see the setting name, the default value provided in the Amazon Linux 2 AMI kernel, and some tuned values which I've developed based on my other work with AWS customers. In this experiment, we will tune the TCP socket buffer values in order to increase the amount of memory assigned to things like the TCP socket buffers. This has the effect of taking the handbrake off TCP and allowing the congestion window to open up to sizes beyond what is permitted by the default settings. You may also notice that there is a tuning option which lists an alternative TCP congestion control algorithm. The congestion control algorithm is the code which tells TCP how to behave during startup phase as it tries to rapidly expand its congestion window, and then which metrics to use and how to behave in its steady state and congestion avoidance phases. TCP cubic is the default Linux kernel TCP algorithm. You may also wish to experiment with a newer algorithm called TCP BBR, which can give better performance under certain conditions. Due to the limited time available for this experiment, we'll only be testing with TCP cubic and adjusting the kernel values for TCP socket buffers. I've also provided some references at the bottom of the slide which may be of interest if you want to learn more about different tuning options for the Linux kernel. For reference, I've included this slide which shows an example of how you may configure the experimental settings shown on the previous slide. As I said before, please do be aware that these settings may not be suitable for your particular application, and also that if you do experiment, please do so in a test environment. This slide shows how TCP cubic congestion window behaved when transferring 1 GB of data from AP Southeast 1 to US East 1. Firstly, as you can see, with the default settings, this transfer took around 150 seconds and was very stable, giving us a flat line across the lifespan of the connection. However, after tuning, it took around 90 seconds. This shows that we could expect a 30 to 40% performance improvement in this particular scenario. In terms of TCP throughput, in the test shown, this rose from around 55 megabits per second to around 90 megabits per second as a result of tuning. What we can also see from the graph, that with the tuned settings, the congestion window was much more active, trying to expand its transmission rate, but responding to signals of congestion in the network. In practice, this meant that the tuned kernel was trying to be more aggressive in its transmission, and as a result, did incur more lost packets, so had to reduce its transmission rate quite often. Overall, around 1,000 packets were lost by the tuned kernel, mostly during the initial startup phase, compared with 0 packets lost with the default settings. Overall, this experiment shows that we can use simple TCP tuning techniques on our EC2 instances to improve the potential throughput of our applications at the possible expense of increased packet retransmissions due to loss. In this case, we got a good improvement, but it's worth reading around the subject and watching some of the relevant reInvent sessions, such as the one linked earlier, to get some ideas which might work for your particular environment and traffic profiles. To conclude, in this session, we've shown how you can improve the performance of your cloud applications by adopting architectures, services, and infrastructure options which reduce latency and thereby increase responsiveness and throughput. We've also shown how you can further tune your infrastructure for stability or performance by using kernel tuning techniques. Thank you very much for your attention today, and I hope you found this session useful and interesting.